3, 2, 1. Good morning, everyone. Welcome to the Toronto Geometry Colloquium.
This is a weekly web series all about geometry processing. This colloquium aims at promoting young researchers and researchers from traditionally underrepresented communities. Every week, we will have an opener talking about their cutting-edge research for 10 minutes, followed by a headliner giving us a keynote presentation.
Today, we are thrilled to have Rosa María Sánchez Banderas as our opener to talk about robust Eulerian on Lagrangian rods, and Xiaodong Wei to discuss his research and analysis of word subdivision and trimming. Please leave all your questions in the YouTube chat. We'll be moderating it and asking them at the end to the speakers. So let's begin with our opener. Rosa María Sánchez Banderas is a PhD student at the Rey Juan Carlos University, advised by Professor Miguel Otadui. Previously, she received a master's degree in computer graphics, games, and virtual reality from the same institution, and a bachelor's degree in multimedia engineering from the University of Valencia. Her research focuses on simulating the behavior of cloth at the yarn level, and the results of her papers are, and specifically the one she's presenting today, are visually astounding. I remember being amazed when I was in the SIGGRAPH audience. She's also our first speaker based in Spain, which means that she's currently living with average temperatures of about 20 degrees Celsius higher than us here in Toronto, which makes me wonder, why did I ever leave? So you can go ahead, Rosa.
Thank you very much for the introduction. Let me share my screen. Okay. Just a second. Okay, can you see my screen?
Yeah, it works great.
Okay, perfect. So thank you very much to everyone for attending. Today I'm going to present you our last work, Robust Eulerian and Lagrangian rods. This is a work done in collaboration with Alejandro Rodriguez from SETI Labs and Héctor Barreiro and Miguel Otadui from University Rey Juan Carlos. Well, as a motivation, objects with rod-like structures are very common in our lives. And due to this fact, they have attracted the attention of computer graphics researchers for many years. But their simulation poses a very challenging problem, especially because many of them are usually found in complex contact situations, which makes complicated the correct detection and resolution of collisions. In the literature, rods, strands, or deformable curves in general have been simulated using different methods. Earlier works present different formulations for describing rod dynamics, but all of them have one thing in common. They handle contact detection and resolution explicitly, which poses challenges in terms of robustness and efficiency. In recent years, new approaches have emerged to handle contact implicitly under certain assumptions. Out of these, the most relevant ones are those based in the Eulerian or Lagrangian method. But they are not able to represent multiple stacked contacts out of the box due to the intrinsic degeneracies in the contact geometry, which basically makes the simulation unstable. So in this work, we propose a method to simulate complex rod structures and stacked layers of cloth with implicit contact handling using Eulerian or Lagrangian discretizations. The method we present handles contact degeneracies robustly, without using remersing techniques, allowing us to simulate stacks of rods sandwiched between sliding contacts with nodes constantly crossing each other. The key to our solution is a new type of mixed Eulerian-Lagrangian discretization node that, combined with the standard EOL discretizations as appropriate, enables the robust simulation of such complex scenarios. And finally, to demonstrate our approach, we demonstrated using on different challenging simulations of yard-level cloth, such as stack layers and complex knit patterns. But before describing our method in detail, let's review a bit the advantages of using Eulerian on Lagrangian methods and the problems that can arise when using this representation. To better illustrate it, consider the following example with an elastic rod, shown in blue, and two rigid sticks that are in contact with the rod. EOL methods track contact points both in spatial and material domains, simply by placing nodes at contact locations. And this is done through two sets of coordinates, the classical spatial or Lagrangian coordinate x, and the material or Eulerian coordinate u. The addition of the Eulerian coordinates allow the nodes to slide in the material domain. But keeping both Eulerian and Lagrangian degrees of freedom free makes the kinematics of the rod suffer from ambiguities. So to solve them, we can simply constrain the Lagrangian coordinates, forcing the nodes to remain at the contact point. And as we can see, this discretization allows efficient and accurate sliding motion at the contacts, but it's still not free of problems. As the two sticks in contact slide along the rod, they may become very close together in the material space. And when this happens, the difference between material coordinates approaches zero. This makes the stiffness of the internal energies tend to infinity, which basically end up making the simulation unstable. And this problem can be tied to degeneracies in the discretization. Previous works avoid these situations by simply remeshing the geometry. In the case of rods, this process is as trivial as collapsing the nodes. But this approach is not viable when the nodes represent sliding contacts. The Eulerian degrees of freedom must remain independent to allow the contacts to cross each other. And as far as we know, no prior work shows any situation where sliding contacts get arbitrarily close and cross each other. Here is where our key contribution comes in. To robustly handle these degenerate situations, we introduce another type of mixed Eulerian Lagrangian node that has some important properties. The first one is that it has only a free Eulerian coordinate, as this property is key to correctly capture sliding. Then we define its Lagrangian coordinates as the interpolation between the adjacent nodes in the segment, making it a Eulerian with interpolated Lagrangian node, or EIL. And this linear interpolation produces geometric properties that makes this new EIL node transparent to the internal rod forces. The first one is that the node does not contribute to the computation of bending energy, as the interpolation constrains the Lagrangian position to lie in the segment defined by the nodes A and C. And second, the strain epsilon of the stretch energy is the same on the two segments adjacent to the EIL node. So the energy can be measured directly using the two adjacent nodes. As a result, even if the Eulerian distance between this EIL node and its adjacent nodes becomes short, there is no negative effect in the stability of the simulation. Finally, the contact constraint cannot be enforced trivially at this new node because its Lagrangian coordinates are not degrees of freedom. So we need to explicitly enforce this constraint. And using our new discretizations, nodes can slide and cross each other robustly, even when degeneracies appear. And how is this new node applied in our simulations? Well, our strategy is simple. We replace with EIL nodes the regular EOL that produce degeneracies. We have a simple heuristic for doing this, but please refer to the paper for more details. As for the actual definition of rod energies, we follow the model of Thirio and colleagues. And finally, as we said earlier, Eulerian with interpolated Lagrangian nodes requires the explicit addition of the contact constraint. So we enforce it by using a soft constraint with large stiffness. And to demonstrate our method, we applied it to jar level cloth. In this case, we first evaluate the performance when applied to multiple layers of jar level cloth. In these cases, the rods pile up in complex arrangements and require constant updates to the discretization to correctly handle the degeneracies. Let me emphasize that in all of these examples, there is no collision detection and no explicit contact handling between the layers. All contact is solved implicitly thanks to our mixed Eulerian-Lagrangian discretization. In this scene, we show the simulation of a back pocket. We pull the pocket from the top and the bottom to introduce sliding. And this fabric is modeled at the yard level at a realistic resolution with a total of 645,000 of nodes. In this example, we show the simulation of a neck tag of a shirt subject to different modes of deformation. And in the last example, we compress the tag to demonstrate that our method is also capable of allowing the different layers of cloth to separate. We also show some examples of stacked tablecloth layers with different friction properties. In this case, with 3 stacked layers, the number of simultaneous EIL nodes can be as high as 35% of the total nodes. In the close-up, we can see how the discretization is constantly changing. And despite continuous sliding and changes, our simulation method handles contact and friction correctly. And we also simulate complex knit patterns with slip stitches. For these experiments, we draw inspiration from the work by Leaf et al. Here we show the relaxation of 2 different patterns under both tight and loose knitting. Although the tight knitting case produced very complex contact configurations, it's also handled correctly. Again, in the close-up, we can see in detail how the yarns slide as the patch relaxes, crossing and sliding over and under the loops. Well, our formulation also enables us to scale up these scenarios without compromising robustness. So to conclude, let us summarize again the contributions of our work. We extended the Eulerian-Lagrangian rod simulation to robustly handle complex contact arrangements with sliding and crossing contacts. Our solution handles degeneracies in a simple and elegant manner, and its implementation brings only small changes to previous methods. As shown in our experiments, these situations appear in diverse practical scenarios, including the simulation of complex knits and contact between multiple layers of cloth. Of course, our method has limitations. We have discontinuities in energy and momentum because of the discretization changes. Although we didn't see any artifacts from those. Another limitation is that certain scenarios may require the dynamic creation of contacts, which could translate into having to add explicit detection of collisions. And finally, we believe that this method could be applicable to other domains, such as thin shell cloth. And that's all. Thank you.
Thank you very much, Rosa. That was an amazing presentation, and the results are just breathtaking. I have so many questions. If all of you watching had any compression artifacts and didn't manage to see the animations well, you can look at Rosa's work at her website, Penguin Code /Rosa, that I'm going to post on the YouTube live chat. And I encourage you to also look at all the other amazing stuff that she does. So now let's move on to our headliner talk. We'll have a joint Q&A at the end. Xiaodong Wei is a postdoctoral researcher in the chair of numerical modeling and simulation at the École Polytechnique Fédérale de Lausanne in Switzerland. He has a PhD in mechanical engineering from Carnegie Mellon University, a master's in civil engineering from the University of Tokyo, and a bachelor's degree from Tsinghua University. Dr. Wei is a perfect fit for a colloquium, since his study of computational geometry and computational mechanics from an engineer's perspective is something at least I don't hear from that often. His work in computer-aided design, about which we'll hear about today, is both mathematically very sophisticated, but also very grounded in practical applications, which frankly makes me think that we, in the more computer science side of things, are getting away with something, because sometimes we don't have any of those two. So it's an honor for me to introduce Xiaodong Wei to the colloquium. So you can take it away.
Okay, thanks very much for the kind introduction. Let me share my slides. Okay, thanks again for the kind introduction. And I also want to thank the organizers for inviting me to give a talk in this wonderful series of seminar. It's really a great pleasure to participate. Given the topics of the seminar, I will talk about two widely used techniques in computer-aided geometric design, which is subdivision and trimming. And in addition to the geometric perspective, I also want to add another perspective of physics-based simulation. So the title of the talk is Analysis-Aware Subdivision and Trimming. This is a joint work with many collaborators, including my PhD advisor, Jessica Zhang from Carnegie Mellon University, my postdoc advisor, Annalisa Buffa from EPFL, Tom Hughes from UT Austin, Xin Li from University of Science and Technology in China, Pablo Antonin from EPFL, and Benjamin Marcid from University of Technology at Graz. And this research work is funded by European Research Council as well as Swiss National Science Foundation. Here's the outline of my talk. First, I will briefly introduce isogeometric analysis, which is a very active research area, and also sets a background of why we need the geometric modeling to be suitable for physics-based simulation. And in this bigger context, I will talk about two specific methods that can model complex geometries. Those are analysis-aware subdivision and analysis-aware trimming. We know that modeling complex geometries is really a substantial step to move forward to deal with real-world applications. And then in the end, I will conclude this talk, hopefully just in time. Okay, let's start. So what is this isogeometric analysis and why we need it? To answer these questions, let's take a step back and see how engineering designs are proceeded. It starts from shape design using some computer-aided design software or CAD software, which gives us a smooth and usually quite complicated, complex shapes. And in this geometric representation, although usually you don't see it, but actually there are many gaps or overlaps hidden in the geometry. And on the other hand, we want to do some physics-based simulations using, for example, finite element analysis to evaluate this design of the product. So we want to estimate or predict some certain mechanical or thermal behaviors of this product, such as solid mechanics, heat transfer, fluid dynamics, or acoustics, all these physics. But such analysis needs a watertight geometry. And on the other hand, this CAD model usually is not a watertight geometry. That means we need to do some pre-processing for this original CAD model. And such that we can create a so-called analysis suitable geometry. And this involves actually many work, including such as to remove those overlaps or gaps and to remove certain geometric features like those holes and the fillets. And eventually we want to get, we will get just a linear approximation to the original smooth geometry. So we will use such a mesh for physics-based simulation. And this is a so-called meshing process, and it's indeed very time-consuming, and it was estimated to take over 80% of the overall time in the product design. Not to mention, if we want to optimize our original design based on the physics-based simulations. So that means we need to go back to the original geometry, then make some modifications, repeat this time-consuming meshing process again and again. On top of this, nowadays, engineering designs are becoming more and more complex, meaning that it involves more and more mechanical components in a single design. So this meshing process is really a bottleneck in current industrial practice. So people decide to do something, and then isogeometric analysis was proposed to tightly integrate computer-aided design with physics-based simulation. And the goal is to eliminate this time-consuming meshing process. To do this, the idea of isogeometric analysis is conceptually simple. It directly uses this smooth geometry, CAD geometry in simulation. In other words, fundamentally, it uses basis functions that used to represent this smooth CAD geometry in simulation. So fundamentally, the difference between finite element analysis and isogeometric analysis is their basis functions. Now, let's take a close look at how these functions are different. First, in isogeometric analysis, it uses the so-called B-splines or NURBS. NURBS is non-uniform rational B-splines, kind of extension of B-splines. And it's also the standard in current commercial CAD systems. And in a word, B-splines are higher order piecewise polynomials. And the most appealing feature of such functions, such polynomials, is their higher order smoothness, as we can see from the graphs of these functions here. It also has some other nice properties, like these functions are non-negative, and if we sum up all these functions, we always get one, which is called partition unity. And each B-spline function only has a local support. All the basis functions are linearly independent, so they can form a basis. These are very, very nice properties of B-splines. On the other hand, in finite element analysis, we use another set of polynomials, which are called Lagrange polynomials. And such polynomials are only globally C0 continuous, as we can see around these regions around the arrows. We can see there's only C0 continuity over there. And the basic functions can be negative, but it also has, these functions also have same properties as B-splines, such as partition unity, local support, linear independence, and so on. But the key takeaway message here is isogeometric analysis uses smooth basis functions, and finite element analysis use non-smooth basis functions. And this fundamental difference also leads to different numerical performance. I will talk about it later. Okay, now with these smooth B-splines, we talk about how the geometric representation looks like. Actually, we can have a geometric mapping by simply taking a linear combination of these B-splines, and the coefficients in such a linear combination are given, and they are called control points, as you can see in these red points. And as a result, we can get a smooth B-spline curve represented here in this black curve. The curve is smooth because the B-spline functions are smooth. It's also straightforward to extend this B-spline curve representation to B-spline surface representation through a tensor product extension. Here, this unit square represents the parametric domain of a B-spline surface. And in this parametric domain, we have the two-dimensional B-splines defined. In each parametric direction, U or V, we have a set of B-spline, 1D B-splines defined as before, and a 2D B-spline is just a product of two 1D B-splines. So then with these 2D B-splines, we can again have a geometric mapping by taking a linear combination of these once we are given a structured grid of control points, as see these red points again. And the B-spline surface is also smooth. Okay, this is a geometric representation. And let's now see what this smoothness means for numerical performance. And indeed, it means superior numerical performance. More specifically, it means improved accuracy stability, and robustness. And more importantly, it opens the door to solve high-order partial differential equations, or PDEs. We know many physics are governed by such equations, and so it will have a significant impact in science, computational science, and engineering. Traditionally, with a finite element method, usually this is solving such a high-order partial differential equation is challenging because their basic functions. Because to solve such functions, we need a high smoothness in the basic functions, which a finite element analysis doesn't have. A typical example of such equation, PDE, is called the Kirchhoff-Love shell formulation. Actually, this is a very efficient shell formulation in engineering work. It's a fourth-order PDE. It needs smooth basic functions. So before IGA was proposed, this formulation was almost never used. And now with IGA, we can use this shell formulation to solve problems on such a B-pillar. B-pillar is an important mechanical component in the car, and we can achieve the same results as finite element analysis, but just with half of the degrees of freedom, which is a significant boost in accuracy and efficiency. This is just one example of success of IGA. Its isogeometric analysis actually has been successfully applied in many challenging problems, such as solid mechanics, fluid dynamics, and fluid structure interaction. Of course, there are many challenges to be addressed in isogeometric analysis. One of the most challenging problems is modeling of complex geometries. One typical way to model complex geometries is to use so-called unstructured control meshes as opposed to structured control meshes. In B-splines and NURBS, recall that we have a tensor product extension from 1D. So there we always have such a structured control mesh. On the other hand, by unstructured control mesh, we mean unstructured correlateral mesh that involves so-called extronal points. And external point is a point that is shared by other than 4 elements. So here see these red points. All of them are shared by 5 elements, so they are external points. And on the other hand, in the structured mesh, every interior point is always shared by 4 elements. So this is the definition of external points. And dealing with unstructured control meshes in isogeometric analysis relies to deal with external points. From the geometric point of view, we need smoothness around the external points, and from the analysis point of view, we need the underlying basic functions to have certain desired properties to have a good numerical performance. Okay, motivated to address this challenging problem, we propose a method which is a subdivision scheme that uses unstructured control meshes to achieve some good performance in both geometric modeling and isogeometric analysis. So subdivision itself is not a new idea, and it can be dated back to 1970s when Cadman-Clark subdivision was first proposed. And yet, this simple idea is still widely used today, even especially in computer animation. And here I use Cadman-Clark to introduce a general idea of subdivision. Here, given this initial mesh, by subdivision, we mean we recursively refine this mesh using some predefined subdivision rules. Then we can get finer and finer meshes. And in the limit, we will have this limit surface, which is globally smooth. Alternatively, people have also derived basis functions associated with such intermediate mesh. Then with such functions, we can directly get that limit surface without repeatedly refining the mesh. So base width can give us the same limit surface. And we know that Kellman-Clark subdivision is a generalization of bi-uniform B-splines to arbitrary topology. Arbitrary topology basically means it supports unstructured control meshes. And being uniform means every edge in the intermediate mesh has the same parameter called knot interval. And these knot intervals are used to define the subdivision rule. But in the uniform case, since they are the same, actually it has no influence on the subdivision rule. But in the non-uniform case, and these knot intervals will be used to define the subdivision rule. When we use subdivision in geometric modeling or other geometric analysis, we need it to be compatible with NURBS to gain more flexibility, and because NURBS is the current standard in CAD systems. So this basically means we need the subdivision scheme to support non-uniform knot intervals. And there are some existing methods that work on non-uniform subdivision, but generally they may produce poor shape quality when used in geometric modeling. This is because they will have like multiple local maximum around the external points in the non-uniform setting. And this is determined by their subdivision rule. So, and another problem is these existing methods do not have a rigorous proof on the G1 smoothness. Basically means a tangential plane is continuous. So without this proof, we don't know for sure that if their limit surface is continuous or not, it is smooth or not. Then on top of this, when we use subdivision in isogeometric analysis, one biggest problem is that we can't solve PDEs with expected convergence. This means this expected convergence means when we do some simple benchmark problems from theory, we know that the area should reduce in a certain rate when we refine the mesh. But when we use, for example, Kellman-Clark functions in simulation, we don't have this. As we can see here, we can only get much worse than the expected rates. So this means there's something insufficient for Kellman-Clark functions. And these functions are purely determined by the subdivision rule. So we need to come up with some novel subdivision rules that are suitable for both geometric modeling and isogeometric analysis. Motivated to address this issue, we propose the method called hybrid non-uniform subdivision. And here is an overview of some properties of this method. First, it extends bicubic NURBS to unstructured control meshes. So basically it means it supports non-uniform knot intervals. And even in the non-uniform setting, this subdivision, when used in geometric modeling, it can give us geometries that have a good shape quality because it can guarantee a single maxima around the external point. Most importantly, it has rigorous proof on this G1 smoothness. And when we use it in isogeometric analysis, we can achieve optimal convergence. Oh, okay. Next, let's see how this method works exactly. Hybrid non-uniform subdivision has two sets of rules: a topological rule to change mesh connectivity and a geometric rule to update the coordinates in the refined mesh. We start with this topological rule. The input is an unstructured correlateral mesh. And based on this mesh, we first create a so-called hybrid mesh by replacing those external points with some polygons. And to make the resulting hybrid mesh conformal, we also further replace certain edges and points with some correlateral faces. As a result, we can see here we have this hybrid mesh. Next, we do the subdivision for such a hybrid mesh. Recall that for Kellman-Clark subdivision, it's directly applied to this input mesh. So this is the key difference. And at the element level, when we do subdivision, basically we want to refine the mesh. There are three types of refinements for elements. This all depends on the configuration of knot intervals. So basically, for some because for some polygons we don't refine them because all the knot intervals are 0, and for some like elements with edges with all non-zero intervals, we subdivide it into 4 elements and so forth. So eventually, we would have this kind of refined hybrid mesh, and we recursively do this. This would be similar to Cadman-Clark subdivision. Okay, this is a topological rule that determines the mesh connectivity. And next, we need to determine the exact positions for the points in the refined mesh. This is a geometric rule, which is also the key rule for the subdivision scheme. And the key here is to compute the polygon vertices in the refined mesh, as indicated in this dashed circle. And we compute this refined polygon vertices as a linear combination of the given polygon vertices. Here is a formula which it looks very complicated. You don't need to understand the details. The key message here is it's like because these coefficients in the linear combination sum to 1, it's like we are shrinking this given polygon to a smaller one. The coefficients in this linear combination are determined by 2 factors. One is knot intervals in the neighboring mesh, and the other is this critical parameter lambda, which controls the extent, which controls how large we shrink this given polygon. So this lambda is really a very important parameter. I will talk about in more details in later. Then here I present the most important theoretical result in this work. That is, the limit surface of a hybrid non-uniform subdivision is G1 continuous, is smooth. This is true all because of the nice properties of the subdivision matrix. Based on the subdivision rule, we can immediately get this subdivision matrix on each element. Back to this critical parameter lambda, we find that this lambda is actually the second and the third eigenvalues of this subdivision matrix. And the subdominant eigenvalues are the most important quantities in a subdivision scheme. They determine the surface continuity, and when we use the subdivision functions in isogeometric analysis, it also influences convergence. And we also note that we actually have some flexibility to choose this lambda as long as it's in this range. But according to some trials and errors, we find that when lambda equals to 2.26, this value, we have a good balance between the quality of geometric mapping, geometric modeling, and the convergence behavior in isogeometric analysis. Okay, next, let me show you several examples. First, we apply hybrid non-uniform subdivision to geometric design, and we compare our results with some existing methods. First, for this, first we use some existing method from this paper. Then we for this helmet model, we find that the shape, the geometry doesn't look that smooth in the left-hand figure, and we also plot the reflection lines on the right-hand side. Reflection lines are popular means to show the quality of a geometrical representation and basically shows the change of surface normals. And if we have reflection lines are more uniform, then we would have a better shape quality. But as you can see here in this red box region, there's some very sharp change in the reflection lines. That means the shape quality over there is not good. On the other hand, if we use our method to model the same geometry, then the geometry looks more smooth, and the reflection lines also look more uniform. So we have a good shape quality. The reason why we can have this good shape quality with the hybrid subdivision is that hybrid subdivision can guarantee a unique maximum around the external point. And the other existing methods usually do not have this property. And this unique local maxima really has a huge impact on the geometric, on the shape quality. Next, we want to, we apply this hybrid subdivision to isogeometric analysis. Basically, we want to test the convergence behavior. So here we only consider very simple but a typical problem, which is Poisson's problem. Then we solve this problem on a unit square domain represented by this unstructured mesh. We also change the knot intervals for these associated with these two red edges so that we can have a non-uniform knot interval setting. Now we summarize the convergence results. We find that in all the cases, we have this optimal convergence. So this is also the promise of our method that can deliver optimal convergence when we use their functions as a basis in isogeometric analysis. And we solve the same problem, same Poisson's problem on this on another domain. Again, we can have this optimal convergence rates. So to summarize, hybrid subdivision, hybrid non-uniform subdivision is can deliver when used in geometric modeling, it can deliver higher quality shapes, and when used in isogeometric analysis, it can achieve optimal convergence rates. So we say this subdivision can be used in both geometric modeling and isogeometric analysis. Up to now, we have been talking about methods that can use unstructured meshes to model complex geometries. In CAD systems, actually, there's another option to model complex geometry. This is through trimming. But usually, trimming is used for used as a visualization means. When we use it in simulation, we need to do some further treatment to make it work properly in analysis, in simulation. And so next, I will talk about analysis aware trimming. Trimming is universal in CAD systems because the solid modeling in CAD systems extensively use trimming. And a solid in a CAD system is usually represented by a BREP or boundary representation. That means only the skin of a volume or the boundary of the volume is described for visualization. And this boundary, this BREP, is a collection of spline surfaces, and these spline surfaces may be trimmed. So when in this kind of representation, we don't have any information about the interior domain of the volume. This is not a problem for geometric modeling because we only care about the shape. But when we do physics-based simulation, this is a huge problem because we need the description of the interior domain to, for example, assign material properties. Without it, we can't do a meaningful physics-based simulation. In fact, trimming is a challenge, even if we only consider to model a surface. Here shows a graphics view of this B pillar. Everything looks fine so far, but if we show it with all the information we have, then we realize there is like thousands of trimmed surfaces, and these surfaces, this geometry representation is messy, and it has many gaps and overlaps hidden in the geometry, and we can't use such a geometric representation directly in simulation. So we need to do something about it. But before I talk about the treatment of trimming in the context of isogeometric analysis, I'd like let's first take a look at how trimming works exactly. Originally, giving a geometric mapping from a parametric domain omega hat to the physical domain omega, then we get this original surface patch. Then by trimming, we actually only restrict this parametric mapping to active subdomain. So in this way, from geometric point of view, trimming only hides parts of the surface invisible to the users, and it is used only for visualization, and it doesn't change anything else. From the analysis point of view, the computational domain will be this omega A, this new phase, rather than the entire phase. And back to the parametric domain, we also realize the parametric domain is no longer a simple rectangle shape, and it may have a quite general shape. And this general shape gives us some challenges when we use trimmed geometries in analysis. And the first challenge is about numerical integration. In finite element analysis or in isogeometric analysis, we need to compute certain integrals on elements. And we do this using some standard numerical integration scheme, such as Gauss quadrature. But such a standard scheme only works for like regular domains, such as triangle, such as a quadrilateral element or triangle element. As we have seen that the trimmed domain may have a general shape, so there's no integration scheme that works for such a domain. And we need to do something about numerical integration. On the other hand, trimming cuts not only the geometry itself, but also it cuts the underlying basis functions. As trimming can be quite arbitrary, so we may end up with a basis function that has a really small effective support. And this small support basis function will give rise to the so-called stability issue. Stability is a very important condition that guarantees that the PDE has a solution, and the solution is unique. So it's a very important condition we need to take care of. In the following, I will talk about basically these two challenging problems one by one. First, as a trimmed domain is generally a high order polygon domain, so we don't have a standard integration scheme. So our idea is to decompose such a polygon domain into, for example, quadrilaterals or triangles, so that we can apply standard integration scheme. But trimming is usually quite arbitrary, so we need to do this decomposition for some base cases. And for the more general cases, we use a divide and conquer strategy. That is, when we have a general case, we split that element until all the sub-elements fall into one of these base cases. And our goal is to achieve a minimum number of integration cells. Here, let's look at these 2D base cases. The idea is to first identify a pair of red curves, and then with this pair of curves, we create a ruled surface between them to serve as the geometrical representation for the trimmed domain. And in each pair of the curves, one curve has to be the trimming curve, and the other curve can have like several cases. It can be a three segment, or several segments, or it can be another trimming curve, or even a point. And when we have general cases, we first split such an element, and we find like all the sub-elements should fall into one of these base cases. Okay, this is 2D. And when we move to 3D, it becomes much more involving, and we will have more cases to work with. But the idea stays the same. It's first we come up with some base cases, which is based on the matching cubes idea. Probably you are very familiar with the idea. In matching cubes, we assume that each edge of a cube can only be cut once. And based on this assumption, we will have several cases. Then for each of these cases, we come up with a specific decomposition for the trimmed domain. And in this way, we do the decomposition. And here is some test cases for the 3D trimmed domains. And indeed, you can see that the trimmed domains have more general shapes. But I should emphasize that accurately representing these trimmed domains has a huge influence on the accuracy and the convergence of the numerical solution. So it's we need to take take it very seriously. Then up to now, we have been talking about trimming in the single domain case, and generally we may have multiple domains combined together to represent a geometry. So this is like a union operation, and for this union operation, we specifically consider overlapping construction. So the idea is the following: given a hierarchy of independent domains, we overlap one on top of another in this way. Then all the bottom patches are trimmed. Then all the visible, so there are some parts of the domains are hidden, and all the visible regions together forms a computational domain. And these independent domains are weakly coupled through their interfaces. Here, weak coupling basically means we need to compute certain integrals on the interface. Again, we need interface. We need an integration mesh to do this job. And in the surface case, the interface between two domains are basically a curve. For example, here the interface of these two domains is basically a part of the boundary of this blue patch, a blue surface. And to create a integration mesh, the basic idea is to find a mesh intersection on this interface. That means we need to find these orange and blue points. And with these points, we can create a interface integration mesh to compute those integrals accurately. And actually here it involves a curve intersection problem, but in the 3D case, there will be a surface intersection problem, which becomes much more involving, and we are still working on it. Up to now, we have been talking about the challenge of numerical integration for both trimmed domains and the union interfaces. And in the following, I will talk about the stability. As I said, stability is an important condition that guarantees the existence and the uniqueness of the solution to a certain PDE. When we have this trimming, and when trimming is arbitrary, we may have the stability issue. That is, we may not have this stability condition. And this is true, especially when we have extremely small effective elements or trimmed elements. For example, here, this red curve indicates a trimming curve. Then we see that these elements marked in light gray are badly trimmed elements. And if we have such kind of elements, we may have stability issue. And to deal with stability, we need to deal with this stability issue, we need some kind of stabilization method. And as this stabilization method are problem dependent, so here we use academic problem, which is Poisson's problem, which with Nietzsche's formulation. And here I give the weak form, but you don't worry, you don't need to understand the details of this formulation. What you need to know is it is these red terms that causes the stability issue. And these red terms are actually the normal derivatives from the trimmed side. And to do stabilization, actually what we do is to replace those terms with their stabilized version. And here I will skip the technical details because it will get very complicated. But instead, I will show you an example on how stabilization influences, for example, important properties like conditioning. Okay, here we consider a simple example that can be easily controlled in terms of trimming condition. Here we have two overlapping domains, and we use that parameter epsilon to control the trimming condition. When we have a smaller epsilon, we will have a worse trimming condition. Then we plot the condition number with respect to this parameter epsilon. We observe that with stabilization, the condition number, see this blue curve, the condition number almost stay the same, no matter how small this epsilon gets. On the other hand, if we don't have proper stabilization, then the condition number will blow up. We know in finite element analysis or isogeometric analysis, in the end, we will need to solve a large linear system of equations. And if the matrix has a bad condition number, we may not get a meaningful solution. So this is a very important property, and we should use stabilization when trimming is involved. Okay, next we study some complex geometries. We want to use our tool, our treatment of trimming and union, to efficiently model such complex geometries. Here, there are several domains involved, and we use trimming to capture those small holes. And on top of such a geometry, we solve the linear elasticity problem. And here shows the displacement results of displacement and stress distribution on the deformed geometry. So here the message is we can use our method to efficiently represent complex geometries, and we can also do physics-based simulations on top of such complex geometries. Actually, with the idea of trimming and union, we can move one step further to combine so-called immersed methods with boundary fitted methods to leverage the average advantages of both methods. One key feature of immersed method is it doesn't need a conformal mesh from the computation domain. Instead, it embeds the boundary of a geometry to a regular Cartesian grid. But immersed methods needs a lot of special treatment along the boundary because the Cartesian grid doesn't align with the geometric features. Then we propose a method that combines the two ideas, the immersed methods with a boundary fitted method. So instead of directly embedding that boundary of the geometry, we first create a boundary layer for this boundary. Then we embed this layer to the background mesh. And then we have this kind of geometrical organization, which involves the trimming and the union. In this way, we can still achieve geometric flexibility from immersed method because we don't create a conformal mesh for the entire domain. And because of this boundary layer, we can easily control mesh resolution around the boundary because it aligns with the boundary features so that we can have higher accuracy. And here we show, okay, we can indeed use this idea to deal with complex geometries, and we can also easily refine the mesh around some key features to better capture the solution features. Okay, in conclusion, I have presented isogeometric analysis, which is one of the most active research areas of finite element analysis and computer-aided design. In this big context, I have presented two methods that deals with complex geometries. One is called hybrid non-uniform subdivision, which we have shown that it's suitable for both geometric modeling and isogeometric analysis. And the other way of representing complex geometries is through trimming, and we mainly talked about their treatment, particularly on numerical integration and stabilization. The examples I show here is basically in 2D, but many ideas can carry along to 3D, and we hope we can make it work in 3D very soon. Thank you very much for your attention. I'm happy to take any questions.
Thank you, Xiaodong. That was a great presentation. I learned a lot. It's a different perspective to what I'm used to. And everyone that's watching, you can learn more about Xiaodong's research interests in his website. He actually has a research tab with like explanations of the projects he's working on and relevant publications. So I'm going to post this on the YouTube chat so anyone can watch it, can see.
Thank you. Thanks.
So we have a bunch of questions for all of you. We're running a little late, so I'll just go straight to that. We'll start with Rosa so that Xiaodong can get like a glass of water or something after talking that long.
Yeah.
So Rosa, I have a question. This one's from me. You say that there are problems when in other methods that aren't yours. You said there are problems when two contact points are like very close together, right? And my question is, does this like spiral out of control even when they're reasonably close, or are we talking like if it reaches that numerical precision, and if I had a reasonable mesh and good numerical precision, that never happened? Like I see your animations and they look amazing, but I'm wondering what would happen in that like cool Sigraph cloth example that you stretch if we hadn't used your method. Maybe I just don't know enough about simulation.
These instabilities appear when the distance between the nodes is reasonably close, even if it's still far from the limits of numerical precision.
Oh, okay.
And if we didn't apply our method, what you will see is either that or the solver will not convert, or the cloth will simply explode. We have really nice simulations just exploding. And this is mostly because very small and highly stiff rod segments lead to very badly conditioned systems. In our examples, we describe the problem with stiffnesses because, yeah, it's very sensitive to small changes whenever the nodes become closer. But this is also true with the systems matrix, for example. And this is a known problem in simulation that's usually fixed by using remeshing techniques. But yeah, in our case, we cannot do that because otherwise we will not have the nodes crossing each other.
I see.
So yeah.
Okay, thank you. That's okay. That explains. So I guess I should look more at the simulation literature. It would be fun to see the animation with it exploding. Okay, so the next question is for Xiaodong. You talked about B-splines and nerves, which, like, at least in our lab, is not something we're used to seeing that much. We usually work with triangle meshes. So I guess this question is, should we just use that from now on? Should the graphics community be working more with B-spline surfaces and nerves instead of just focusing on triangle meshes? And a more general question is, like, what is the limit of this surface, and can we do things, use them in simulation, like solving elasticity problems on them?
I mean, using triangle meshes, these linear meshes, to solve problems, right? Your question is, actually, that's what I think there's the motivation of isogeometric analysis to use these high order functions is to tightly integrate this computer-aided design, because in this design we use high order things, and to tightly integrate these things, it's rationale to use these smooth functions rather than to introduce an intermediate step that is meshing to get these triangles. I mean, of course, the community of mesh generation is huge, and there's a very elegant, nice algorithm in that field methods. So I mean, it's of course good for you to work also on these smooth surfaces if you can, but if you have interest. But I mean, there is a lot of nice things about triangle meshes itself. So yeah,
right.
They would coexist at the same.
Okay, so it's peaceful coexistence then. Good. So another question for Rosa. We seem to have a Sigraph reviewer in the chat or something, because one question is, what's the runtime like? What will it take to bring this closer to real time?
Well, unfortunately, these simulations are still far from real time. I don't remember the exact numbers, but it's in the order of tens of seconds, more or less. But the large amount of degrees of freedom makes it a pretty challenging problem. Even with a GPU implementation. The Pocket, for example, is modeled at a realistic resolution with 645,000 of nodes, which is a lot. But yeah, I think that to accelerate it further, we will need to be smarter on the solver side. Maybe give better initial guess to make sure it converts faster, or maybe with machine learning techniques could be useful in this regard. But yeah, it's still far from real time.
Okay, that's great. And that marks 64 minutes until someone said machine learning, which is, I think, our record for this colloquium. So the next question is for Xiaodong. You, in the design or behavior prediction setting, there's error from numerical method and also error from modeling. So the digital shape, the forces, or the materials don't necessarily match the real world counterparts. Where do we currently stand in the relative values of these errors? So is one of them, can we discard one of them or with respect to the other?
Yeah, right now, I think, in real applications, we should consider these systematic errors. But when we develop these numerical methods, what we care about is really the numerical performance. It's like we assume, okay, our model is perfect, under this perfect setting, okay, and what we want, what we develop can reach some expected results. That's our way of developing these methods.
Okay, thank you. So that's I think a good answer. This was a question we had in the YouTube live chat. Okay, so that's a wrap for today. We're a little over time. We'd like to end by thanking our artist, Jian Liv, who designed this week's amazing 3D poster. It's our first 3D poster. So this was the last episode of season 1 of our colloquium. So you can stay tuned for a return in season 2 in the next couple of months. I can personally say it's been a lot of fun being part of the organizing team, and I'd be remiss if I didn't end this season by thanking the many people that made this colloquium possible, starting from everyone at the University of Toronto DGP Laboratory and the graphics group. I'd like to specifically thank Honglin Chen for accompanying me today, Josh Holinati for working as our unofficial art director and reaching out to all the amazing illustrators that made our posters, the amazing illustrators who made stunning works of art every week and helped us build a unique identity in this colloquium. Obviously, all our speakers who put in a lot of effort into creating great, engaging presentations for you every week, as we've seen again today with both of you. I'd also like to thank Professor Alec Jacobson for advising in organization, as well as, of course, my usual co-hosts, Derek Liu and Sanbei Bang, who couldn't join me today, with special warm wishes for Sam Bang and the newest member of their family, who is doing great, but doesn't have a name yet. And we wish them the best. Finally, I'd like to thank you all for watching. Whether you watch us live or watch our recordings on YouTube, you are really what keeps this colloquium going. Thank you very much, and see you in season 2.
Thank you.
Okay, that was it.